To start working with the normal vector, what I'd like to do is just to take a plane in space and then think about, so we'll just take this as some plane z equals z0, and then just have a circular path on that plane. Okay? So that this is going to be my trajectory r of t. In space, what we would like to do, so now we know about how fast a curve is changing in space. We want to talk about the direction the curve changes in space. In other words, if I draw a tangent vector at some point and then sometime later create another tangent vector like this one. Okay? So as we go around that circle, that tangent vector is constantly changing, and we want to know or want to quantify the amount by which it changes, or the direction in which it changes, right? Remember, that's a vector. So there needs to be some component that's pushing this trajectory towards the path, and so that component is this normal component that we'll call the normal vector, right? So these are at right angles, and it allows my path to continue on into space, so that our unit normal vector of arc length points in the direction that the tangent vector is changing with respect to arc length. So that's dt ds. Okay, so that what we want to think about, is the definition now, is in thinking that, okay, so if we can be shown that the dot product of the tangent vector and the normal vector is 0, so that these two are orthogonal, right? So far we have two components to create these three-dimensional system. Okay, so that the important things to remember is that it's orthogonal to the tangent vector and that it points towards the inside of the curve and moving around. There's some definitional parts of that. So that if we define now that unit normal vector as the change with respect to the tangent over its speed, right, the typical way of making a unit vector, but we know that the curvature is that magnitude of that change with respect to arc length. So that therefore we get a definition that unit tangent vector is 1 over kappa times the change in the vector. Okay, so that's very useful. So for parameterized curves, that's our definition, right? So we've kind of seen, and we've struggled a little bit with the idea that, oh, well, we're going to have to talk about arc length, so we do that. But if we have other curves, we can also define it in a similar way. N of t is then dt over that magnitude, right? And that just keeps us in the parameter frame, and we can use either one of those. Okay, and so just depending on whether we have a parameterization for our curve or not. Okay, so what I would like to do is to look at the next step, which is to take an example of a new figure. Sorry about that. What I want to do is turn this one off. No, there we go. And go up to this one. And so that now what we want to talk about is this helix. And so a helix is a figure in space, right? So if I put that figure in space here, let me just label my axes, X, Y, and Z, is that in a two-dimensional projection, if I was to project this figure onto the X and Y plane, it would look like a circle, right? But that circle is parameterized by, here's my vector, or my trajectory, r of t, and the parameterization of my circle is a cosine, a sine, so we know that this circle has a radius of a, and that the component that is going to create the helix is the b of t. So let me just break down my values here. So the parameter is going from infinity to infinity. We're going without bound, positive real number, positive real number. Okay, so that now as I draw this helix, is that I'm going to just start an arbitrary point here and then continue on as it goes up in B, right? So that value of B is the stretchiness, or how sparse this is done. So that to complete this calculation, I'll need the velocity and its magnitude. And then in addition, one more, to do these two parts is to calculate the unit tangent vector. So that's my immediate goal here, is to compute the tangent vector. So then its magnitude is then, of course, we take our magnitude of our derivative, and we'll do the square roots and find out that it's a squared plus b squared. Okay, so taking these two pieces gives us the unit tangent vector, and so that t, the unit tangent vector, is then going to be t of t is our ratio of our values here, and that find out that it is the vector, where are we here? So t is then that vector, minus a sine t, a cosine t, b, all over the speed. Okay, so there we go. So there's our unit tangent vector. So we need that to figure out what is happening, or we need that to figure out the normal, but we also needed to kind of think about what this value means here as we go along, right? So we still have our circular components, but now a constant value of the z component, so that this unit tangent vector is along this curve pointing in an upwards direction at a constant value, that constant slope amount that's allowing me to say, okay, well, I'm continuing up at a constant rate. Okay, so the unit tangent vector is kind of telling us how that behaves. Okay, so that now we need the next calculation is then to calculate how that tangent vector is changing with the value of the parameter. In other words, I need to calculate dt. So to do that, I'm just going to kind of write this out as in notation here, is that I take the derivative of this vector that I just computed, and the denominator is a constant, so we don't need the quotient rule or anything like that. And we can find out that this value is minus a cosine, minus a sine, and 0, all over that speed. Okay, a squared plus b squared. Okay, so then if we calculate, if we calculate the magnitude of that, we'll just end up with our value a over a squared plus b squared. Okay, so look what would happen if we did go ahead and calculate that value, right? So that the magnitude should be the sum of squares. So here I would have a squared cosine squared, a squared sine squared, and then 0. So I end up with the root of a squared, which comes out to be my value of a. Okay, so that now we can finish up and calculate our normal vector. And we do that by just putting the pieces together that we've already found, right? So I'm just going to put the definition down here one more time over its magnitude, t, dt, and then as a calculation looks a little complicated, but that's a minus sine a sine t and 0 over the speed, and then in the denominator we'll have a similar thing, a over the speed. Okay, so that once we end up with it, we'll find out that this normal vector will complete simplify the calculation, minus cosine t, minus sine t, and 0. Okay, so that's a calculation of the normal vector for a helix. So what I want to do finally is then just check that value and make sure that I have the two pieces that I need, that I know that I need in the way that the normal vector behaves. Number one is that the tangent vector and the normal vector are orthogonal. Okay, so that's my first task here, is to figure out, or is to check that these two things are true. Okay, so here is my tangent vector, and I have the first component that would get dotted is a, and I get an a cosine, and in this component I'd get a minus a cosine, and in the last component I would get 0. Okay, so that all works out, that it all cancels, that works. The second thing that I should check is that it truly is a unit normal vector. Okay, well here's if I took the magnitude of this vector, I'd get a cosine squared, I get a sine squared, I get a 0, and that adds up to 1. Okay, so I have found successfully the unit normal vector, and now have two of my three components that I need to create a T and B frame.